Hello and welcome to Physics 142. We're beginning this semester by studying simple harmonic motion. This may be a review to some of you who've seen this topic before, but it's the foundation for our study that will begin next week of wave motion. So let's begin. A simple model consists of a mass, m, connected to a horizontal spring and free to move across a horizontal surface without any friction. So you see my diagram here, and this is just a model. There's lots of different kinds of oscillating systems in nature, but this is perhaps the simplest way that we can analyze mathematically a system like that. And you see in my sketch the object's equilibrium position, where it would be if it were at rest and not stretched, where the spring's not stretched or compressed, would be at x equals 0. So we're imagining pulling the spring to the right a distance x, and then releasing it. But at this point, we can write down Newton's second law and then figure out what the equation of motion is for this mass and solve that equation of motion to come up with an expression for the position as a function of time. And it's quite remarkable that we can do this in terms of just the mass of the system and the spring constant k. So first, to do Newton's second law, we have to know an expression for the force that the spring exerts on the mass, and that is something that is given approximately for simple springs by Hooke's law. And we encountered Hooke's law in the first semester of the course. In Latin, Robert Hooke wrote down, I'm not sure about my Latin pronunciation, but it's something like ut tensio sic vi, and that means as the force, so the displacement. And so the horizontal force in this case is equal in magnitude to the spring constant times the displacement. So it's linearly proportional to the displacement. If the displacement doubles, the magnitude of the force doubles as well. But the minus sign is important, and that tells us that this spring force is a restoring force. It always pulls the mass back toward the equilibrium position. So, for example, if x is positive, the force is negative. All right, with that in place, we can write down Newton's second law for this mass spring system, for the mass moving horizontally. It's forces along the y direction. There's a normal force upward and the gravitational force downward. Since it doesn't move along that direction, those two forces are equal in magnitude, and we only have to worry then in terms of the motion of the system about the forces in the x direction. So the sum of the forces in the x direction is equal to mass times the x acceleration. The only force in the x direction, if we neglect friction, is minus kx. That's equal to mass times acceleration, which is mass times the first derivative of velocity, and that's the same as mass times the second derivative of the position with respect to time. So if we just rewrite this equation, solving for the second derivative, we get d squared x dt squared equals minus k over m times x. And this, that comes directly from Newton's second law, is the equation of motion. It gives us a relationship between this displacement x that we're trying to solve for and some derivative or derivatives of that quantity with respect to time. So a solution to this equation of motion would be an expression for x as a function of time that would tell us where the object is, where this mass is at all points in time. Now this is a differential equation, and as such, it's in general, differential equations are quite tough to solve, but this is a special kind of differential equation, and we notice that it tells us the second derivative of the function x is equal to a negative constant times the function itself. And there's only certain kinds of mathematical functions that behave that way. The two that we know about already through our study of trigonometry that describe things that oscillate back and forth are the sine and the cosine function. And so if we were to take these two trial solutions, x equals the constant a times the cosine of a constant omega times t, or the same kind of expression with a sine function, if we plug those into the equation of motion and set the two sides equal, we would be able to show that those expressions work. The cosine or the sine terms cancel out, and they leave us with the relationship that says this quantity omega is equal to the square root of k over m. Now, a few definitions about these terms. The a that is in here is the maximum value that the position can have, and as such we call that A value the amplitude. It's a length if x is a position. And then omega, since omega times t has to be a unit that has dimensions of radians, then omega is a kind of frequency because it has units of radians per unit time. And although there's no hint here that we're describing circular motion, we call that an angular frequency because omega tells us at what frequency the angle that's in the parentheses changes. And finally, when we actually write down the most general solution to the equation of motion, it's given by x equals a times the cosine of omega t plus a phase angle phi. And the reason that the phi is in there is because x could be a pure cosine function, or it could be a pure sine function, or it could be something in between those two. And so having the phase angle phi in here gives us the flexibility of describing a function which is neither a pure cosine or sine, but somewhere in between. And so phi has units of radians, because everything that's in parentheses has to have the angular unit. So this is a solution to that differential equation, and it's pretty much the answer to every question that we might ask about that oscillating mass connected to the spring. A tells us what its maximum displacement is, that's the amplitude. Omega tells us the frequency of oscillation, and then phi tells us, depending on its value, whether we have a pure cosine or sine function or something in between. So let me show you an example that's similar to some homework problems that you'll have. This is called an initial value problem, because knowing what the solution is for this mass spring system that undergoes simple harmonic motion, if we are given the initial position and if we're given the initial velocity of the mass, we can use that information to solve for A and omega and phi. Okay, now actually omega depends on the value of k and the value of the mass. But the initial position and velocity will allow us to solve for A and phi, and then we can write down the expression for the motion of the mass, x of t, completely. And we get all of the complete information for that object. So here's an example. 200 gram mass is attached to a spring with a known spring constant. It oscillates with an initial position. Now initial means t equals 0. The initial position is 10 centimeters, but it's not at rest. It has an initial velocity of 20 centimeters per second. Find its position as a function of time. So the way you solve an initial value problem is you start with the equation for the position and the equation for the velocity, and then we know the values that they have at time t equals 0. So we'll substitute in t equals 0 and use that information. So x is given by a cosine omega t plus phi. If we plug in t equals 0, we get a cosine 0 plus phi, which is just a cosine phi, and the problem statement tells us that that value is equal to 10 centimeters. So here's an equation that involves a and phi, but they're both in the same equation, so we can't solve for either one of them directly, which is why we need another equation. We need the equation that tells us the general form for the velocity of this mass. So taking the derivative of the position, we get minus omega a sine omega t plus phi, and plugging in t equals 0 to that equation, we end up showing that the velocity at t equals 0 is minus omega a sine phi. We're told that that value is 20 centimeters per second, and now we have enough information to combine the first equation that comes from the value of x and the second equation that comes from the value of v. With two equations and two unknowns, we can combine those two equations and solve for a and phi. I'm not going to do that here, but hopefully that illustrates the principle behind the solution to an initial value problem. Now let's move on to talk about a discussion of simple harmonic motion from the energy perspective. Rather than just look at forces and positions and velocities and accelerations, let's look at the energy of this object as it oscillates back and forth. So if we write down the expressions that we know about for the kinetic energy and then for the potential energy that's stored in the spring, we can substitute into this equation our expressions for x and v that were written down on the previous slide. So remember, these are the two expressions here that I'm going to substitute into the equation for the total energy of the mass in the spring system. So the The v squared term is given right here in parentheses. We have the minus omega a sine term, and that whole thing's got to be squared. And then the second term, 1/2 k times the expression for x squared. All right, so we do a little bit of arithmetic here, and we find out that the omega squared comes out in front. There's an a squared out in front, and there's a sine squared term. And then over here, 1/2 k a squared times the cosine squared term. All right, and it doesn't look obvious that we can simplify that anymore, except remember that there's a relationship between omega, k, and m. We showed that on a previous slide. The relationship was that omega squared is equal to k divided by m, which means that m omega squared is the same thing as k. So realizing that, we can rewrite this expression for the total energy, now seeing that there's a 1/2 ka squared in front of the sine squared term and a 1/2 ka squared in front of the cosine squared term. So if we factor that out from the two terms, we end up inside the brackets with sine squared plus cosine squared. And no matter what the value of t is or the value of phi is, as long as the t and the phi are the same in those two arguments, sine squared plus cosine squared will always equal 1. So what this shows us is, although as the mass oscillates back and forth, it exchanges kinetic energy and potential energy. The kinetic and the potential energies do indeed change with time, and we can see that here in the expression for the total energy. But the sum of the two is equal to a constant that only depends on the spring constant and on the amplitude of motion. So the larger the amplitude, the more the energy is. The larger the spring constant, the more the energy is. But this total energy is a constant for the system as long as there's no kinds of frictional forces that would tend to make the energy go down. So this is an important expression, and we can do a simple example that is quite a nice one that allows us to relate energy to the position and to the velocity. So here, let's say that we're told that when we have an oscillating mass spring system, half its energy is kinetic, of course, which means the other half is potential. And we would like to know, at that point, what's the displacement of the mass? It might be tempting to think that the displacement of the mass would be half of its amplitude, but it turns out that that's not correct. So we can simply solve this problem by turning the given information into an equation. What does it mean that half of the energy is kinetic? Well, half the energy is kinetic. It also means that half of it is potential. So half of the total energy is kinetic means that the kinetic energy is half of the total energy. And as I said, since we're trying to find information out to answer this question about the displacement, about x, we would like to actually use some information about the potential energy, since the kinetic energy is related to the velocity, but the potential energy is related to the position. So if, of course, if half the energy is kinetic, then we can see by subtraction that U, the potential energy, is the total energy minus the kinetic energy, which is half of the total energy, right? Since K is half E, then U is also half E. And using the expression for U, we know that that's equal to 1/2 kx squared. What does that mean? Well, we can't solve for x yet in this equation because it's in terms of E, and we don't know what E is. However, we have an expression for E that we just learned. So if we substitute in that E is equal to 1/2 Ka squared, right? Then 1/2 E is 1/2 times 1/2 Ka squared, and that's equal to 1/2 Kx squared. And now we can solve this expression for x and get it as a multiple of K. So just simplifying what's on the left-hand side, 1/4 Ka squared is equal to 1/2 Kx squared, and solving that for x gives us that x is equal to a over square root of 2. And we can check this. The units, of course, make sense. One other thing that we can check is that the x value is less than a. A, remember, being the amplitude, is the maximum that x can ever be. And so it would indicate some kind of mistake if we got an x value that was greater than a. But clearly this answer is some fraction of a, and therefore it makes sense. And notice it's not a over 2. It's actually a over square root of 2. So be careful about making invalid assumptions in problems like this. All right, finally, a very, very common system that also undergoes approximately the same kind of motion as the mass spring system is what's called the simple pendulum. The simple pendulum is distinguished by having a mass that is connected to some kind of pivot point through a very, very lightweight string or rod whose mass we can completely neglect compared to the mass of the pendulum bob. And the important variables in characterizing the motion of this system are the angular displacement that it has away from its equilibrium, which would be the vertical position, and the length. That's the variable. Theta is the important variable, but the distance traveled along the circular path, we'll call that S, and geometrically we can realize that that arc length S is equal to the length of the pendulum times theta. Notice that this length would be measured from the pivot all the way to the center of mass of the pendulum bob. Okay, so we're going to do the same thing that we did in the mass spring system and write down Newton's second law along the tangential direction of motion, right? Because in this case, we could adopt the coordinate system where we have a radial coordinate and then we also have a tangential coordinate, and we know that along the radial direction the object doesn't move. It doesn't get any closer to the pivot point or further away from it. It stays at a constant distance L away from that. So its only motion is along the tangential direction, which is instantaneously the motion along this circular arc. So there's a tension in the string, T. That's one of the forces. The other force is the earth pulling down, the weight, so that's mg. Those are the only forces. If we take the weight force and break it down into a component along the radial direction and a component along the tangential direction, we can see with our trigonometry that the important component along the tangential direction is mg sine theta. Notice too that it opposes the direction of theta. So if theta is positive, this mg sine theta is in the negative direction. So we can take Newton's second law along the tangential direction and write it down. The only force acting along the tangential direction is mg sine theta. But, as I said before, it's negative mg sine theta. So the left-hand side, negative mg sine theta, is equal to the right-hand side, which is m times d squared s dt squared. S, remember, measures the displacement along the tangential direction, and so the second derivative of that is the acceleration term. But we'd like to get this in terms of theta because s is related to theta. Remember that s is equal to L theta, and so when we take the derivative with respect to time of this equation, L doesn't change. So the first derivative would be ds dt is L d theta dt, and d squared s dt squared is equal to L times d squared theta dt squared. So we can make that substitution if we just let s equal to L theta, take that second derivative, as I said a minute ago, what we get is ml d squared theta dt squared. Now notice what happens here if we look at the left and right hand sides of this equation, that mass drops out. So the motion of a simple pendulum does not depend on its mass. What we get then, if we take that equation after canceling out the mass and solve for the second derivative of theta with respect to time, we see that that's minus g over L times sine theta. So the motion is influenced by g, which is related to the gravitational force, and it's also related to the length of the pendulum, but the mass is not involved. Now let's compare this equation of motion to the one that we had with the mass spring system. Notice that it's not the same, because in the mass spring system we had the second derivative of x, and then we had minus some constant times x itself. Here, instead of having theta, we have the sine of theta. However, what we can do, because this equation in the exact form that we have in the box is something we can't solve with pencil and paper. We can solve it using numerical techniques, but we can never write down a simple solution the way that we can for the simple harmonic oscillator. However, all is not lost, because there's a Taylor series expansion for the sine of theta in terms of theta itself. And the first order term in that expansion is that sine of theta is approximately equal to theta, if theta has a small value. The reason is that all of the higher order terms are in terms of powers of theta. I believe that the second term would be negative theta cubed over 3 factorial, and the term after that is theta to the 5th, and then theta to the 7th. So if theta is very small, then those higher powers of theta will be even smaller, because anything less than 1, when you square it, it gets smaller instead of getting bigger. So we can make this small angle approximation, substitute into this equation of motion, and get an approximate equation of motion that looks like this. Now when we compare this to the mass spring equation of motion, we see that it's basically the same equation. The variable is theta instead of x, and the constant has the ratio g over L instead of k over m, but otherwise it's exactly the same. And so what we can do is solve this new equation of motion, which we recognize as an approximation, by analogy. Right? Here was the solution that we verified through substitution was the correct solution for the equation of motion for the mass spring system. All we have to do is write down that same kind of solution for the angular oscillations of the simple pendulum. So instead of x, we have theta, and instead of a, we'll call the term out in front theta max, because remember, a is the maximum value that x can have. And so otherwise, it's got the cosine of omega t plus phi. The only difference here is that omega, which for the mass spring system was square root of k over m, is now replaced by the square root of g over L. And I know this because look what happens. K over m in the original equation of motion is replaced by g over L. So instead of square root k over m, I have square root g over L. And so that tells us that in this approximation where the angular displacement is very small, then the simple pendulum behaves just the same way that a simple harmonic oscillator does, like the mass spring system. Hope this helps as an introduction to harmonic motion. And there's one more thing I want to do before finishing, and that is to just take a moment to talk about the relationship between angular frequency omega, the what's sometimes called the conventional frequency f, and then the period t. All three of these quantities are distinct, but they're all related. So if we know one of them, we can easily calculate the other two. So just as a review, remember that the angular frequency omega is angle measure per unit time, so it's got units of radians per second. Normal frequency, f, that's just the number of cycles per unit time, so it has units of cycles per second, which we call Hertz. That's a special name, named after the German physicist Heinrich Hertz. And then period is the time per cycle. So we can see right away, while frequency is cycles per time, period is time per cycle. So those are very closely related to each other. In fact, they're just reciprocals of one another. So if I know the frequency, the period is simply 1 over the frequency. And since omega is in radians per second and f is in cycles per second, since I know that one cycle is 2 pi radians, I can use that as a conversion factor to relate f to omega. And so just by inspecting the units, we can see that omega is 2 pi times f, because f would be multiplied by a conversion factor 2 pi radians per cycle, right? And t is 1 over f. We talked about that a minute ago. So we could also substitute in for f here and relate t to omega and realize t is 2 pi over omega. So these are expressions that we have to use sometimes to relate these three quantities. Realize, of course, that if you have one of them, you can find the other two. So, hope that serves as a good introduction, and I will see you in class.